for some students' requests. So keep it clean. All right. So just a reminder about the schedule. Well, I guess the main thing is that there's an exam on Wednesday of next week. Since there's an exam on Wednesday of next week, on Monday we will review. So as I told you last time, there are okay. So there are review materials posted on Moodle. Take a look at those before Monday, see what you think. You guys just gave me homework yesterday. I'm hoping to have that graded by tomorrow, so by tomorrow evening. So in terms of homework corrections, if you want to do those, that homework set you just gave me over chapter 6, that will still be due before this next exam. There's also a chapter 8 homework set, which due to our compressed our compressed time window here, that's not going to be due to Wednesday when the exam is, as we've discussed before. So of course I can't give you formal grading on that before the exam. So if you want to correct chapter 8 homework, you can have until the final exam to do that. But because the exam covers chapter 8 and I can't give you feedback on it in a timely fashion before your exam, if you have issues with that, you should ask on Monday or shoot me an email or something. So if there's anything in chapter 8 that you think you wouldn't be able to do on an exam, you have to let me know. So you can either ask on Monday or you can ask over email or in office hours on Tuesday. All sorts of times you can ask, and you should ask. Okay, so in summary here, I'll have your chapter 6 homework graded by tomorrow evening. I'll probably grade a lot of it tomorrow evening while my kids are parked in front of the TV. So you can look at that, correct that before Wednesday. But the chapter 8 homework, I won't be able to do that for you. Okay, so any questions on the schedule or what we did last time or anything before we finish off chapter 8? Okay. As always, if you have questions, you should just shout them out. So the chat, for some reason, when I share stuff, the chat's not always showing me things. So like right now I can see it, but sometimes I can't. So if you have an issue, make sure you shout out. Also, as always, I can't see your faces, so I don't know if you're confused or not, or even if you're there. But if you are there and you're confused, you should let me know. Okay, so let me go over here. Okay, so section 8.4. Oh man, Bayesian statistics. What fun this is. So Thursday fun day, I guess. We're not used to that. So Thursday fun day, I guess, is a proxy for Friday fun day. This is really nice, this Bayesian statistics thing. And there are some schools, and I think my wife's school is one of them, that has an entire class on Bayesian statistics. So there's a lot you could say. And I've had to really sort of control myself. I'm sticking to your book. So your book has this one section. And this one section is really nice. It gives you an idea of how this statistics work. But of course, we're not doing a full course's work of worth. I really butchered that. We're not doing an entire course today, obviously, you know. But this gives you an idea of how Bayesian statistics works. And mostly it's just chapter 6 and section 8.1 just kind of beefed up. And again, it gives you an idea of how you might build an election forecasting model or something where you eat in data, update, and so on. That's what this section is. So I want to do two things before I show you Bayesian statistics. The first thing I want to do is, the second thing I want to do is reset classical statistics. The first thing I want to do actually is sort of review what probability means actually. So I want to take a statement from class last time, and I want you to interpret it for me. I'm not sure why it's not letting me move, but okay, here's the statement we had from last time. The probability O.J. Simpson is guilty. All the caveats here, is guilty just based on only the evidence we had, namely that his wife was murdered and he abused her. But anyway, so there's a lot of caveats you could throw in here, but the probability O.J. Simpson is guilty is 85%. That's what we said last time, just based on the evidence we examined last time. This is a probability statement, right? The probability of something is this percentage. So I want somebody to think back to the very first day of class. The very first day of class, it's been a while. I doubt you can remember it, but we talked about what probabilities mean. So I said, you know, we started with the example of coin flipping, an example everybody knows. The probability is 1/2 or 50%. What does that mean? And then we processed it and talked about it. So I want you to imagine we're on the first day of class and you have to process this statement the same way we did on the first day of class. So somebody do that for me. What does this statement mean? If we were on the first day of class and I forced you to interpret this statement the same way we did in the first day of class, how would you do that?
There's an 85% chance that O.J. Simpson is guilty. Oh, wait, no.
I mean, that's true, but just like on the first day of class, you can't sort of like replace probability with chance just because you're like, you're defining in a circle or something. So maybe actually it's worth, let's put up the example from the first day. Probability of flipping a heads is 50%, or if you like, 1/2. How did we interpret that on the first day of class?
Are you looking for the limit of Hn over n as n approaches infinity is equal to 0.01?
Yeah, right. So that's
0.85.
Yeah. So we said, well, like to process this, what Trent is saying is, imagine flipping a coin over and over and over again, millions, billions, trillions of times, and then you take a limit. The proportion of times you get heads limits to 50%. So I'm not going to write all that English down because we have it multiple times in the notes, but let me just say it again one more time. You have an experiment you're repeating over and over and over and over again, flipping a coin. And then you're asking, well, as I flip a coin, the proportion of times I see heads, where's that going? And the answer is it's going to half. So in the long run, half the time you'll see heads, in the limit. Okay, now somebody take that and apply it to this. If you take the same exact kind of framework and apply it to this statement, what do you have to say?
$85% of if you do this, this 85 times out of, if the same situation applies an infinite number of times, 85, it'll happen like this 85 out of every 100.
Yeah, so what you're saying is correct. Let me just refine it a little bit, because when you say this, let's be clear about what this is. If you imagine Nicole Brown Simpson, or Nicole Brown, I guess as she was known when she was murdered, if you imagine her being murdered over and over and over again, that's like the experiment, So imagine her being murdered millions and then billions of times, and you let that number of times run to infinity. The proportion of times that O.J. Simpson did it approaches 85%. That's what that would have to mean. Does everybody say that? So let me just say that one more time. If Nicole Brown Simpson is murdered over and over and over again as an experiment, the proportion of times that O.J. Simpson did it approaches 85%. Now let me ask you, everything I just said, is that how your brain is processing this number? Is that what that 85% means to you in this context? I can't see your faces, but I imagine your faces. Either you look confused and bored, or you're shaking your head no. That's not really how a jury is thinking about that number. They're not imagining Nicole Simpson being murdered millions of times and then trying to measure a proportion of times her ex-husband did it. So all of this to say, when you're doing this Bayesian stuff, there's actually kind of a sleight of hand that happened here that I didn't acknowledge and that nobody called me on. So shame on you people for not calling me on it. The probability here doesn't quite mean what it used to mean. Now, there's a lot of sort of philosophy here where you can actually kind of make sense of this number the way we did back on the first day of class. But at least on the surface level, what we're doing now isn't really that kind of like repeating an experiment proportional definition. So in this chapter, actually, the way we're thinking about this number, it's more I was going to say colloquial, but that's not the right word. More intuitive or something, more informal maybe. So in this chapter, you sort of have to think about probabilities as quantifying disbelief or quantifying surprise. So if something has an 85% chance of happening, you're not surprised at all when it happens. Does everybody see that? 85% means like it's not surprising if it happens. You're actually kind of surprised if it doesn't happen, but you're not that surprised because 15% is not that small. So you just have to imagine a spectrum from like 0 to 1, where over here, you're like completely shocked, which I think I spelled correctly. If something happens and the probability is like 0, 0.1, you're super shocked that it happened. But here, you're not shocked at all. You're like, oh yeah, of course that thing happened. So you're kind of imagining probability as like a sliding scale of disbelief or surprise, a quantifying of surprise or something. Anyway, so I just did want to acknowledge that that sleight of hand happened and I didn't mention it. One of you should have yelled at me about that. Okay, so that's the first thing to acknowledge. Now, the next thing I want to do is just reset what we did in chapter 5 so I can draw a contrast between chapter 5 and what we're doing today. So here is a classic, all this is a classic chapter 5 hypothesis test thing. So I'm not going to spend a lot of time on it because we did it and you guys took an exam over it, but let me just reset it quickly. So you have a new treatment for a disease. The old treatment has a 35% success rate, not great maybe. And you run a clinical trial, which is very small, but whatever, we take it as a given. 10 patients, and the drug worked on 7 of them. That's pretty good. 70% rate is better than 35%. So the question is, what kind of evidence do we have the new treatment is more effective than the old one? Now, again, as we discussed in chapter 5, on the surface level, it's obvious we have more evidence because 70% is way more than 35%. But also, as we saw in chapter 5, you can't analyze things intuitively like that. Otherwise, statistics wouldn't exist. You have to think about like, well, this 10, man, that's a pretty small sample. So is that really telling you what you want to know? Also, is 70% that far from 35% with such a small sample, et cetera? You have to actually process all that. So here's the processing of it. So again, I'm not going to go through this carefully because we've done it, but you would do a hypothesis test for a proportion, as most of you did on the exam, because you're comparing 70% to 35% given the sample size we have. But I want to be very clear about what we're doing probabilistically. We're saying, what's the probability we see data like this? That's the probability we're thinking about. So we're thinking about probability I see this data, assuming what? The new drug's not more effective. So the new drug has to prove its effectiveness. Okay, so assuming this new drug is not better than the old one, what's the probability you see data like that? This is the p-value we were getting back in chapter 5. So again, it's like a backdoor way, as we discussed over and over again. It's like a backdoor way of getting at what you actually care about. I mean, what you actually care about is this. Is the drug more effective or not than the old one? And the way we thought about it was we asked ourselves, what's the probability I see this kind of data if it weren't effective? And in this case, if the new drug were not more effective, there's a very small chance you would see this kind of data. So whenever the p-value is small, that's good evidence that you should reject whatever the default claim is. And as we discussed over and over again, right, the default claim in a drug trial is that this new drug you made is not effective or not more effective. It has to prove its effectiveness. So you default to assuming it's not effective. That's a classical plan that hits, whatever. I mean, it's still done, obviously, right? So it's both classical and modern. But this is like a classical stats approach to investigating or just sort of like processing this kind of clinical data right here, 7 out of 10. How do you think about that? You calculate this probability over here, this one. So that's what we did back in chapter 5. So let me pause here and ask, it's been a while since we've thought about this, I guess, but is this work here clear? Do you recognize this from chapter 5? As always here, I'm not sure why in the notes I do this, but I have the integral here if you want to see it, for those of you who like calculus, but you can just grab this 0.7 from the normal distribution calculator. So sorry, any questions on this?
We're good.
Okay. So by way of motivating what we're going to do next, let me now point out that there are many drawbacks to this approach. And they're not like mathematical drawbacks so much. It's not like there's a problem with the math or the logic, but there are problems with people interpreting what you've done, things like that. So what are some of the drawbacks of doing this? As we discussed back in chapter 5, this p-value you get, we decided that we're going to reject if we get less than 1% or 5%. Those are the classic p-value cutoff levels. But those are arbitrary choices. It's not like God himself or herself said something like, well, hey, guys, just so you know, whenever a p-value gets less than 5%, you should reject things. So like a 4.9% p-value, reject. But a 5.01 p-value, you keep that, but you don't reject. There's nothing telling us that. So like 5% versus 4%, like what's so special about 5? People just like multiples of 5, don't they? And what about 1%? Like why not put a cutoff at 0.8%? It's arbitrary. And arbitrariness seems kind of bad. So all that to say, there's like, when you get a p-value, there's a lot of gray area. And the gray area is kind of big. Like, suppose it comes back at 8%. Do you reject? We say no, but 8% is kind of small. I don't know. What if it comes back at 0.1%? I mean, 0.1% things happen sometimes. So you're going to reject? Anyway, all that to say, these cutoffs are arbitrary. As we saw, as many of you saw in your exam, right? These p-values can indeed be difficult to interpret. So when you present your data to people, if they don't have statistical fluency, it's hard to know what to do with that 0.7%. Mainly to the point of Bayesians here, what we care about in this section. If somebody just asks you, what's the probability the new treatment is better than the old one? We have to shrug and say, I don't know, man, because I didn't calculate that probability. I was just thinking like yes or no, right? More effective, not more effective. And now I think it's more effective, but I can't give you a probability because the probability I calculated, again, this is like the 2 millionth time I'm going to say this, but we're not thinking about the probability the new drug is more effective or not more effective, whichever. We're thinking about the probability I see data like what I saw. So probability of doesn't apply to the claim. It applies to the data, which then helps you think about whether the claim is true or not. But that's a binary choice, right? Claim true, claim not true. And finally, the last drawback here, well, suppose you run another clinical trial and now you get some other hit rate, whatever. How could you kind of like eat that into the previous trial you did? It's not clear how you do that. Now you can do it, but it's beyond the scope of this course. It's not easy. So all that to say, I mean, of course, people still do this, right? This is a classic thing to do. And you can find p-values and like, I mean, whatever, those vaccine trials for COVID. But there are some drawbacks to this. So Bayesians say, how about we don't have these drawbacks? Doesn't that seem like a good idea? All right, let's get rid of these drawbacks and do something different. And in particular, Bayesians are like, I don't like this drawback here. I don't want to think about probability of seeing this data. I want to think about probability of the claim itself. Like they want to think about what's the probability the new drug is more effective than the old one. They want to give a probability to that. So that's what they do. So I'm going to show you how that works. Now, what I'm going to show you here, it does take some getting used to, and you have to do it a couple of times, but at base level, it's just a chance tree that you're pruning. So what we're doing today is not new. It dates back to section 6.1 probably. So this is just section 6.1, but like on steroids or something. So you can already start to see from the notation can be a little hairy here, but all we're doing is adding up branches that are in a tree. So don't be intimidated by all the text here. Really, there's just a chance tree here. We're going to prune it because we've gotten some data, and then we just do what we did back in chapter 6. That's all that this is. So it looks intimidating, and it is until you try it, but it's not so bad once you do it a couple of times. Okay, so as I said up on the previous page, the Bayesians want to know, hey, what's the probability the new drug is more effective than the old one? That seems relevant, and that seems what we should actually be calculating. Okay, so the problem with their approach, as we'll discuss in detail later, is that in order to get this up and running, you always have to specify what are called priors. So you have to think about, well, I don't have any data yet, so I have to assign prior probabilities to my possible outcomes. So in this problem, what is an outcome? An outcome is an effectiveness rate for the drug. So we're going to stick with integers here. You don't have to. If you're building a computer program, especially, you don't have to. But let's just assume that the new drug either cures 36% of people or 37% of people or 38%, so on. So we're going to stick just to integers. So the possible success rates of this new drug range from 0 to 100 by ones. Now, again, if you're building a computer program or something, you don't have to stick to just integers. You could be like 36.01, 36.02, 36.03. You can build as much distance or not distance as you want to between consecutive points. But anyway, for the sake of us, let's just stick with whole numbers here. Okay, so here are the possible success rates for this new drug, anything from 0 to 100, and capital SR denotes those possible success rates, and then little SR denotes a particular one. So little SR can take on the value 1% right now, or 2%, or so on. Okay, so suppose you've just made this new drug, and I ask you, what's the probability the new drug has a success rate of 38%? So let me just write that over here somewhere. Probability success rate of new drug is some number, I don't care, 38%. I ask you, what's that probability? And suppose I ask you this, you've just made this drug. So it just came out of the drug making machine, whatever that is. Okay, I'm not a biologist. I have no idea what the terminology is. But you just have this fresh batch of drug in your hand. And I say, hey, what's the probability of success rate is that? This question mark here is the right answer, isn't it? I don't know. What do you want me to say? I haven't even tested it yet, you know? Does everybody see that? If there's no data yet and this drug is just fresh, how are you supposed to know what a probability like this is? So again, an appropriate response is like this guy. Right, that's you right now, I guess. I can't see any of your faces. So let me just pause and ask, do you guys agree that either one of these reactions is correct right now?
Yeah.
All right, so Jacob agrees. Okay, so again, if you have issues, you got to shout it out. Okay, so the drawback of Bayesian stats is to get the process up and running, you cannot shrug right here. You can't do this. You actually have to start with prior probabilities. You have to start with probability assignments to the various outcomes. So if you're going to do that, what Bayesians say is like, well, I mean, right now we have no information, do we? But here are the possible outcomes. This new drug could be terrible. Could have a 0% success rate. I don't know. I haven't tested it yet. It could have a 1% success rate. It could have a 2% success rate, right? So on, 3%. ... Or the new drug could be awesome, 100% success rate. So there are 101 possible success rates, right? Start counting at 0 all the way up to 100. And if you have no data yet, this is all in a vacuum, you know, and I force you, I say, look, you must give me a probability of this outcome. You must give me a probability of that, and so on. Bayesians say, well, in the absence of any information, I'm just going to assume what's called a uniform distribution. This is what they normally do. So there are 101 possible outcomes. I suppose they're all equally likely till I start learning things. So this, a lot of times, is their prior assignment. So instead of shrugging, you still kind of shrug, but you say, well, there's 101 outcomes. I'm just going to assume they're all equally likely for now. What else am I supposed to do in the absence of any data? And once you do this, we can actually sort of build a tree and almost be done with this example. But let me pause and ask, does everybody understand this, this probability assignment here?
Yeah.
Okay. Now, a reaction you might have is, wow, that seems kind of an arbitrary choice you just made. I mean, you said out loud, like, well, no data, so I guess uniform. But that's arbitrary, you know? In particular, like, suppose this new drug is based off the old drug. Well, the old drugs cured 35% of people. So this might like be impossible. So maybe instead of putting like a 1% probability here, maybe you should put a 0% there. I don't know. And is any drug completely effective? I don't know. Maybe there is one, but so maybe 1% there is not reasonable. I don't know. Anyway, so it's an arbitrary choice you've made. And by the way, Bayesians don't always do this. So as we discussed, whatever day it was, if you're going to build an election forecasting model using a Bayesian setup, your priors are determined by previous years. So you have no data this year, but you have some data from last year and the year before. So you don't start with something uniform because last year and the time before that inform your probabilities. So I forget what day we talked about this, but if you're trying to predict if Trump will win in 2020, and you're trying to do that in 2019, did I freeze? Did I freeze or was I?
No, you're good.
No, you're good.
You're good.
Okay. So back in 2019, you're trying to predict Trump will win. You know, you don't assign a 50-50 outcome to that. Like, it's not like Trump versus Democrat, 50-50. You don't do that. As we discussed in class in 2019, the prior probability of Trump winning is much bigger than 50% because he's an incumbent with a strong economy. So you don't always start with a uniform distribution, but a lot of times that's what you do. Okay, so back to this now. So now we have these probabilities we've assigned. We now have to update them because we have some data, don't we? We ran this clinical trial, and maybe shame on us for only having 10 patients, right? So again, this clinical trial still happened. So 10 patients is not very many, but whatever. You ran a clinical trial, 7 out of the 10 people were cured or the treatment was effective, however you want to say it. So how do we eat that data in? What we're going to do is we're going to build a tree. So let me build a tree for you. And let me get rid of all this, just so I have room. Okay. So here are the possible success rates of the drug. I'm not going to draw all of them, but 0%, 1%, there's a success rate, 2%, 3%, ... 98%. Okay. Now, initially, as we just discussed, you have no data, so you're going to choose to put a uniform distribution on each of these outcomes here. So initially, all success rates are as likely as any other one to show up. So sorry, I don't know if this is readable or not, but this is a 1 divided by 101, as we discussed. Okay, so now you run your trial, and let me just let D be the event. 7 out of 10 are cured, or whatever you mean by effective, right? And so now on this tree, we have 2 branches. You can either see that data or not see that data. Right? Those are the 2 options. Either 7 out of 10 were cured or not. And the not covers a lot of ground, right? I mean, 6 out of 10, 9 out of 10, 0 out of 10, whatever. But every single one of these branches has a branch like this. You either see that data or not. You either see that data or not. See that data or not. Okay, so now the question is, to use this tree, we of course have to fill in probabilities along all these extra edges. And then as a final step, we will step back and say to ourselves, well, I put data or not data, right? Data or not data. But I saw that data, didn't I? I mean, I literally said 7 out of 10. So these branches down here will be dead to us when we actually go to calculate probabilities, because I did see that data, and so on. So eventually we'll prune these branches off. Okay, so now I want to start thinking about probabilities of these edges. So I'm going to highlight one here. Actually, maybe not highlight. Let me just draw arrows to them. Okay, that edge there. Okay, so now the drug is 0% effective, right? If the drug is 0% effective, what's the probability I see this data?
0.
Yeah, does everybody agree with that? If the drug is 0% effective, you don't cure anybody, do you? So there's a 0 there, and there's a 1 down here that we prune off. So that was pretty boring. Let's do something slightly more interesting now. So this edge right here. Okay, now, if the drug is 1% effective, what's the probability I see data like that? So I have 10 patients and 7 of them were cured. What do you think about that? It shouldn't be high, right? But it's not 0 anymore. So actually, let me phrase it this way before somebody answers. There were 10 patients in this trial, right? Each patient is kind of like an independent experiment unto themselves or something, right? Each patient, you give them the drug. This effectiveness rate means there's a 1% chance the drug works on them. Okay, so let me zoom out again and ask this question. You have 10 people. For 7 of them, the drug succeeded. And the success rate was 1%. Whoops, not erasing, but 1%. So does that kind of question feel familiar to you? Because it should. And then does anybody recognize how you'd answer that question?
No idea.
Okay, so that's fine for now.
Isn't it a binomial distribution?
Yeah. So that's fine for now because we did that exam. And once you take an exam, you don't have to remember it anymore until the final. So I guess it's not foolproof. But yeah, this is a binomial question because I have 10 people. So I have 10 independent trials, each one of them given a drug with a 1% chance of success, and then 7 of them succeed. Yeah, so the binomial distribution looks like this. I have 10 independent experiments from which I'll choose 7 successes. Here's the success probability, not very high, to the 7th. Here's the fail probability, quite high. And then there are 3 like that. That's what goes right there. So let me grab this from Wolfram real quick, or if somebody gets it, you can yell it out. But let me just, actually, while I'm doing this, let me pause and ask, do you guys recognize this binomial thing and recognize this as a binomial problem, as Calvin pointed out?
Yeah, I recognize it.
Okay. Anybody have any issues with that? Okay, so the probability is not 0, but it's awfully small. And that makes complete sense, right? Because if a drug has a 1% success rate, that means it's going to cure 1% of it to the patients, right? If a drug has a 1% success rate, you're not going to see 7 out of 10 people cured very often. It's going to happen on the scale of 10 to the negative 12. It's really small, you know? So that's how you decorate the edges of this tree. So if you go to any random spot, like, here, let me do just one more. Let's think about this probability. You still have 10 people in the trial, 7 of whom were cured, so 7 successes. Now for that branch, the success rate, so the success probability is different. So you would just change the 0.01 to a 0.03, and then the fail rate has to go down also. Let me just grab that. Anyway, so here's a binomial distribution up in your face again. So it's a very useful concept. So that was really smart of me to spend some time on it, right? Good thinking on my part. Oops. You people don't compliment me on my forethought very often. And I think that's a mistake you're making because I make brilliant decisions all the time. I also make some very terrible decisions. I'd prefer you not point those out, okay? Only point out my brilliant successes. So as you march through this tree, notice this, this probability here is still tiny, but it's bigger than this one. And that makes sense because if you have a 3% success rate it's easier to cure 7 out of 10 than if you only have a 1% success rate. It's still not particularly easy, right? 10 to the minus 9. Okay, so let me ask you guys this. As you march your way through this tree, which we're not going to do, obviously, because we only have half an hour left. If this were a 3-hour class, I guess we could do it if we felt like it. But as you march through the tree, which of these, and when I say these, I mean these guys, which of these do you think will yield the highest probability? So when you do the math, you're going to get an answer here, right? So which of these success rates will give you the highest of these numbers over here?
$98.
Why do you say 98?
It's the closest to 70%, which is 7 out of 10, I guess.
Oh, yeah, right. So notice the ... here. I just got tired of writing. So 4%, 5%, 6%, those are all in there. And in particular, 70% is in there. Right, in this
Gotcha. ...
Yeah, right there. Yeah, so what you're saying, Shane, is good, right? Like the data suggests a 70% success rate, right? I mean, 7 out of 10. So let's just think about a 70% success rate probability. So probability, the new drug, is that effective? So you do the binomial thing again, 10, 7, 0.7 here, 7 successes, 0.3 here, 3 failures. You're not going to get 10 to the minus whatever anymore. I mean, it's still not going to be huge, but it's like this. So way bigger, right? Okay, so at this point, we actually are truly almost done. If you understand what we did with this, with these little, with labeling of these edges, we can just sort of finish off the problem now. And you understand now the basics of how Bayesian statistics works. So let me pause here and ask if there's any issues with anything I did here, with any of these probabilities I was filling in.
No, I think I understand this.
Okay. Anybody have any issues?
Nope.
Okay, so now let's finish off the problem. Let's think about what we were interested in. We were interested in probability new drug more effective than the old drug.
So would you just do a summation of everything above the
Yeah, good.
old one?
Right. Yeah, right. So we just have to recall what was the effectiveness of the old drug. I forget now. The old drug was like 35% effective. Is that right? Where does it say? Yeah, the old drug was 35% effective. So down here, what we're asking is, we're thinking about probability that your success rate is at least 0.36. So you want to do better than the old one. And then as you say, Trenton, right? I mean, once you identify that, like, oh, okay, well, I know what to do now. I have to cut out these edges that I've already started cutting out, right? These guys are gone. Don't care about them because I didn't see the other data. I saw what I saw. And now, as we've seen with pruning of trees, what you do here is you create a fraction where the bottom is total weight left in the tree. Well, what's the total weight left in the tree? Sorry, 1 second. Yeah, so Ben, since we're dealing with just whole numbers of percentages here, you could phrase it that way also. You could write it like this: probability SR bigger than 0.35. So in this context, these two things are equivalent. But again, if you were actually doing this with a computer, you could sort of like make things continuous here rather than discrete like we're doing. But for us, we're just leaving things sort of discrete for simplicity. But again, like you can take a class on Bayesian statistics, which would involve learning some RStudio and things like that to like do continuous Bayesian stats, but we're just not going to mess with it. Okay, so if I come back here, if I look at the total weight left in the tree, I mean, I got this branch like 0% and then see the data, this branch 0% see data, this branch is so on. So I just have to add up all those. That's what goes in the denominator. In the numerator, I have to put the total weight of what I'm actually interested in. So the bottom contains like everything that's left. The top contains just the things I care about. And again, for me, I care about these guys. I care about 36% or higher. I don't care about 32%, 25%. Those don't correspond to what I'm after right now. So that's all I'm going to do. I'm just going to add up all the branches in here that correspond to 36 or higher, and then divide by all the branches that are left. So when I say I'm going to do that, that's what this handout does. So if you look at the handout, it gives you, yes, where? Okay, so right here. Right here, sorry, I lost it. Okay, so if you want to add up all the edges that are left, you get 0.09, this is saying. So I went through and did like this from the tree. Yeah, so this guy here. Okay, so what do you hand to Wolfram? Like, how did I get this 0.09? Because that's what I handed to Wolfram. You have to set up a summation like this. So what goes right here? Sum from I equals 0 to 100, because we're going from this 0 right here all the way up to this 100. And then we have 1 out of 101, because I have to traverse this first edge. So for every one of these guys, I traverse this first edge like that. And then what comes next? What comes next is whatever this blue probability is. There. But you can start to see the pattern, right? What is that blue probability? Well, it's like the success rate here, and then 1 minus it there, and then a 7 and 3 there. It doesn't really change. So here I would just have to ask Wolfram to do this. I would have to do 10, choose 7, success rate, but since these are, sorry, I keep forgetting that when I point at things, you guys don't see it. Forget that. We're going over integers here, right? So when you're dealing with rates as decimals, you have to convert them to decimals. So oops, I over 100 raised to the 7th, 1 minus I over 100 raised to the 3rd. So this here is the probability of 7 out of 10 being cured with that success rate. So looking at the handout, I'm not sure why I didn't put the summation in there unless I'm missing it. But anyway, that's the summation that you get. And all that's left from that is 0.09. So there's not much weight left in the tree. We snipped off 91% of the tree's weight. But whatever, that's our new denominator. So all of that, this comes like that. So let me just, I know it's obnoxious to watch people scroll, but let me scroll back over here and just see, did I put that somewhere? So I have it written formally right here, but I guess I didn't actually write it out somewhere. So see, that's going from 0 to 100 and just following the branches that are left. So that sum is doing. Again, it's going this branch, this branch, this branch, and so on. This branch never follows the green. These green ones that got nicked off, gone. This branch. Okay, so sorry, again, I don't know why I don't have this exact thing in that handout, but there's your denominator. You add up all the weight that's left. Questions on that? I should say, by the way, that on an exam, the most common mistake is to forget this, actually. because you do have to traverse these first edges here, right? You do have to go through those to get to the later probabilities with binomial. So if you forget that first edge and you don't have that 1/101 there, the final answer gets like crazy, you know, because you're not dividing by something here. Any issues with this? Is this summation understandable, or should we go over it again? Since I don't hear people saying anything either way, I suspect this might not be understandable. So if there's some issue with the sum, you should let me know. Let me start going through just asking. The index here going from 0 to 100, is that understandable? Is that clear where
Yeah.
this came from? Okay.
Yes.
Is it clear where this came from?
Not entirely.
Okay, so back up here, my tree is now a mess because I messed with it so much. If you're gonna, sorry, if you're gonna snip off these edges down here, now you have to add up the total amount of weight that's left in the tree, which means you have to walk this edge, then walk that edge. So that's 1/101 times 0. Then you got to walk this edge followed by that edge. That's 1/101 times this thing we got.
I think what I'm most confused about. So what I'm most confused about is why it's 101 on the bottom, I think.
Like instead of 100?
Sorry.
Instead of 100, or what do you mean?
Yeah.
So yeah, so since 0% is a possible outcome, as is 100%, there are actually 101 different outcomes. So if you start counting,
Okay, that makes sense.
one.
Thank you.
Okay, and then is this understandable here where this came from? This is the probability of seeing 7 successes given whatever your current success rate is. There's your current success rate as you're adding up. So let me make my picture or my work even messier here. I'm going to highlight this. Is that clear where that's coming from?
Yeah, I think so.
Can you just say where it comes from quickly?
Yeah, sure. So in this yellow, you're now assuming the success rate is I. So let's just say 50%, right? So let's say that right now in the sum, I is 50. So now you're saying, oh, I have a 50% success rate. So now what's the probability I would see that data that I got? 10 out of 7. So there's your classic binomial of like, okay, if I have 7 cures out of 10 experiments and my success rate is 50%, here's the binomial probability of seeing that happen.
So that second bit's just binomial from our first exam thing.
Right, yeah.
Right.
Yeah, so you need 7 hits out of 10 tries. So here's the number of ways of just choosing 7 from 10. And then here are your 7 hits with that success. And there are your 3 misses. So you have to include the 3 misses also. And there's the probability of missing on 3. So yeah, we haven't talked about binomial for like a month, but that's what the probability is. Okay, so now I'm going to finish off the problem by writing everything in its full glory. So here's 0.09 down here. That's all the weight that's left in the tree. Now up top, you have to think about the total weight of what you're actually interested in. So you're interested in things that are 36% or higher. You don't care about things that are 5%. You're not interested in that right now. So up here, you just go back to Wolfram and you say, hey, Wolfram, for right now, I care about from 36 to 100. Otherwise, everything's the same. So when you get your numerator in a problem like this, it's just you keep your denominator, whatever you typed into Wolfram, keep it up, like don't close the window. So here, right, you care about 36% success or higher. That'd be more effective. And now if I go back over here to the work, yeah, see, here's 36 to 100, and there's my 1 out of 100. I'm not sure why I wrote on the right that time. Here's the binomial, and then dividing by the thing I already knew, and you'll get something like 98.7%, up to rounding and things. So you have some big sum up top, and then you expand that big sum on the bottom. Right, just go from 0, not from 36 to 100, but from 0 to 100. And you compare those two things, and that's your probability. So again, I'm not sure why Zoom takes so much longer than actually in class. It seems like it'd be the opposite, but so we're running a little short on time here, but let me just say, it looks intimidating, probably because of summations. So it is intimidating, but generally speaking, the students don't have any trouble with this by the time the exam rolls around, because it is just kind of like, it is just this tree pruning. So once you do it like once or twice, it's much more natural. So before I try to wrap up or maximize our last 10 minutes here, I guess, right? Any questions on this computation that we got at the very bottom? So when we finally finish things off.
I'm good.
Okay. So notice there is a problem here. I'm not sure if there's time for you guys to try it right now. So maybe we should save that for Monday if you want to. So let me just say a few things, and we'll see if we have time to maybe try this. Just some drawbacks of this approach. The prior distribution was arbitrary, as we discussed. So I won't say anything more about that. That's a drawback. Anytime something arbitrary, I don't know, it can feel off. Also, as we discussed, the word probability doesn't really mean what it used to. So you have to get used to that. Now, some of you didn't like the way it was defined before. So I guess this works out for you because this is more informal. Now, the last thing I want to say before I see if we have time for this last example is that, okay, way back up here, see this drawback 4? Suppose you now run another clinical trial and you want to incorporate that data in. The classical statistics way, it's much harder to do than this way. So now, after your first clinical trial, you can update your priors as follows. So before, I mean, it hurts my eyes to go back to my original picture, so I won't show the whole thing. But before, remember, in the absence of data, we assigned probabilities like that. Now we have some data. You know, we've eaten some data in, so we can update that. So now if you start decorating these edges, there's like a 0 right there. Given the data we had before, we know the effectiveness rate is not 0%. And what was 1? 1 was like this thing, 1.16 times 10 to the negative 12, and so on. Wait, is that what it was?
I believe so, yes.
Oh, sorry, that was just this little decoration right here, right? So the probability of getting a success rate of 1% is actually like this, very tiny. Because this guy here was just that final edge. So anyway, you'd put that new thing here. Like it's basically 0 again. Now 70% by contrast is like a ... 70%. That's not 1 out of 1 out of 1 out of 1 anymore. Right, that's been updated. It's much bigger now. We got a value of like 0.26 or something. Where was that? Yeah, like much bigger. So if you're doing this in practice, every time you eat in a new study, you just update these edges right here using the technique we just did. So update that edge, so on, update that edge. So some of the edges get bigger, some get smaller as you eat in the data. And of course, the edges that get bigger, whose probabilities go up, are the ones closest to the data, as Shane said half an hour ago. So it's just very easy to eat data in, especially if you have a computer programming running. You know, you just teach the program to prune these trees for you, prune the branches, and it can update probabilities for you very easily. So that's a big advantage over the previous chapter 5 stuff. Okay, so we have 7 minutes left. So what I want you to do is see if you can modify. I think there's time, because once you set up the sums, at least set up the sums, and we can maybe get an answer on Monday. But at least set up the sums for this. So what you need to do is imagine, again, these are the possible success rates of your drug. ... So for any of these problems, the tree is always the same. It's like this. Data or not that data. Data, not that data. So what I want you to do is think about what the summation would be here. So you're going to have a big sum on top with a limited range, and then a big sum on bottom where the range goes from 0 to 100. So take like maybe 3-4 minutes to think about what those big sums would be. Does everybody understand what I'm asking you to do for a couple minutes?
Yeah.
Okay. Okay, so we only have about 3 minutes left, so let's at least fill in these sums. And if you want to get the answers, again, we can get them. Oh, well, the answer is here, 10%. But we can talk through it in more detail on Monday if you want. So let's get the denominator sum. That always goes, in this case, from 0 to 100, because that's the full range. So what we need to write next is our prior probability. That comes here, because that's the first branch you traverse. So in this problem, what's the prior probability now?
It would still be
Isn't it the
101
same?
101, right?
Yeah, we still have no data at all, right? So in the absence of any data, this is what you do in these problems. Okay, so now here, now we got to think about, okay, the binomial thing given whatever I is, right? So before we had 10 choose 7, 10 choose 7 right there, right? What do we have now?
30 choose 16.
Yeah, you got 16 out of 30 hit. And the success probabilities, though, are still the same, I over 100. It's just, what's the exponent now? What goes up there?
16.
Yeah, 16 hits. And then here are all your failures. And there you go. Is that okay with everybody? Similar to the other example? And then what changes up top? So if you're going to do the top sum, you want to know the probability that you're successful, where successful means at least 65%. So in the bottom, I went from 0 to 100. Where does I start now?
65.
Yeah, it still goes to 100, but otherwise it's the same. Same as the bottom. You're just taking it like a subset of what's left and comparing it to what's left. Okay, so again, sorry that we have this time crunch at the end. I don't know how time slips away so quickly on Zoom. Time flies when you're having fun over Zoom, I guess. But anyway, so on Monday, what you should do is look over the old exam, look over those review problems. I'll have chapter 6 graded for you, so you can ask questions about that if you want to. But really, you should be focusing on, of those review materials, what am I going to stumble on? Because like with other old exams, right, I'm not particularly trying to hide what I'm going to ask from you. So any of those problems, if you identify things you're going to stumble on, you need to send me an email or ask on Monday. All right, so I'll see you guys then.
Thank you.
Yep, see ya.
Thank you, Dr.
Yep, see ya.